Welcome to this second lecture of this week. So in this lecture we are going to try to learn about the DC motor, which is going to be used to convert electrical energy into mechanical energy. So I know that this topic is quite strange for you, but if it is going to console you, I can say that most of electrical engineering students would hate this topic as well, unfortunately. But I want you actually to learn the mathematical model of it, even though you don't understand the physical mechanism that DC motor is working. So here, the mathematical model is not going to be difficult. It's just going to be some linear relationships between voltages and torques and velocities, angular velocities, etc. And once you grasp the main idea of DC motor, it is not really a difficult topic, and sometimes it might be even looking like a puzzle to obtain a mathematical model when the model involves a DC motor. So we will start with the DC motor. I will first draw the electrical model of DC motor, and then we're going to try to understand what is the physical relationship between these circuits and the physical electric motor structure. So we start with DC motor here. So DC motor is composed of two electrical circuits. Okay, so I have a resistance RA here and an inductance LA, and we show the first circuit like this. This is called the armature circuit. Armature circuit. Okay, so we apply a voltage to this one. It is called VA, and we get a current on this wire. It is called IA. When I talk about these voltages and currents, I talk about the armature voltage and armature current. So we are going to see that there is going to be an induced voltage here between these two terminals of the DC motor circuit, armature circuit, and this is called the voltage EB. Okay? It is actually called, in electrical engineering terminology, it's called back EMF voltage, or just back EMF. And this part is somehow connected to an inertia usually, and we have some friction here. This J models the inertia of the rotor of the DC motor. Okay, I will talk about what rotor is and what is this friction is, etc. And the motor generates a torque, and we also have an angular velocity here. And we would like to obtain the relationship between these voltages, currents, and this torque generated by the DC motor and the velocity that we obtain from the DC motor. So in general, this J is modeling the inertia of the rotor, the rotating part of the motor, and B is the friction between that rotating part and its surroundings. So the DC motor has one more circuit that is called the field circuit, and it is usually drawn like this. So I have RF and LF. These are modeling this electric circuit, this second circuit, and the current passing through that circuit is the field current, and the voltage applied to that circuit is called the field voltage. All right? And we would like to understand what this type of model would give us. And this circuit here is called the field circuit. Okay, so both of these circuits are inside a single DC motor. I will talk about which part is actually which. So the basic idea is that we create a field in the gap of the DC motor, and in that in that field, we put some wires into the rotor from which we pass some current. And if you pass some current from a wire inside a field, then a torque is generated by the physical rules. So here, these electrical elements are modeling both of these circuits. So RA is the armature resistance, LA is the armature inductance, LF is the field inductance, and RF is the field resistance. So here maybe I can write some variables here about what they are. VA is the armature voltage. IA is armature current, and VF is field voltage, and IF is the field current. Okay? So these are our variables, and of course these are our parameters in these circuits, resistances and inductances. And I have here an additional voltage that is called EB. As I told you, this is called the back EMF voltage. Back EMF voltage. Okay? We are going to learn about the relationships between these voltages, and this tau is the torque generated by the motor, and omega is the angular speed. So here I can put one more variable here, and that is the variable theta. So I have the theta is the angle of the rotor. Rotor is the rotating part of the DC motor, and omega is the angular speed, angular velocity of the rotor. Okay? And we know that there is a relationship between the angular velocity and the actual angle, or I can here say that angular displacement instead of angle. Let us say it like that. So this is the angular displacement of the rotor. Okay? And there is a relationship between angular velocity and the angular displacement. We know that this angular velocity, omega, should be equal to just theta dot. Okay? This is the relationship between the angular displacement and the angular velocity. All right? So these two variables are related to each other, and I have the torque tau generated by the DC motor. So here first I will talk about what this circuit here means. An electric motor, a DC motor, is in general is just looking like a cylinder. Okay? So I would have a cylinder like this, and here inside this cylinder, there is a rotating part. That is the rotor of the DC motor. So this part is actually rotating. Okay? And there is a shaft connected to this rotor. Okay? So this shaft is then connected to a load here that you can see. So here, the field part, so this part, the outside part, or outside non-moving parts of the DC motor are called stator. Okay? And the moving parts are called rotor. Okay? And on both the stator and on the rotor as well, we have two circuits. And these are these two circuits. Okay? Field circuit is on the stator, and the armature circuit is on the rotor. Okay? So this armature circuit is actually rotating with the rotation of the rotor. Okay? And the stator circuit is the field circuit. So what we do when we use the DC motor is that we apply some voltage to the field circuit. Okay, we apply some voltage. There are some terminals here, and here I apply VF. Okay, we apply some voltage to the stator circuit, which is the field circuit, and we get some field current. This voltage here and this current here, it creates a magnetic field inside the air gap of the DC motor. So the field circuit, when we apply a voltage to that circuit, it creates a voltage inside the air gap of the DC motor. Then what we do next is that we also apply a voltage to the circuit on the rotor. So we apply a voltage here, plus minus, to the circuit of the rotor. But you know the rotor is rotating most of the times. So how can we find the terminals to apply some voltage there? So here there is a device called commutator. In that case, you don't have to know the details here. There is a device or technology that is called a commutator, and by using that technology we can actually apply a voltage to a rotating circuit. Okay? Then what happens is that this field circuit creates a magnetic field inside the air gap. And inside the air gap, we have the armature circuit, which we pass a current through. Okay? Inside the air gap, we have the armature circuit, which we pass a current through. So if you pass some current through a wire in a magnetic field, a torque or a force is applied onto that wire. Okay? Inside in a magnetic field, if you pass some current from a wire, then into that wire, a force is applied. Okay? And that force generates the torque that is rotating the rotor here. Okay? We create a magnetic field by applying a field voltage here in the air gap of the DC motor, and we pass a current from some wires in that magnetic field, and doing that just generates a torque that would rotate the rotor of the DC motor. Okay? So if you move a wire inside a magnetic field, if you have a wire and if you pass it through a magnetic field, if you move it inside a magnetic field, a voltage is induced on that wire. This is the back EMF voltage here that we model as EB here. Okay? This armature circuit is rotating with the rotor, so this armature circuit is moving with the rotor. So if you have a wire moving inside a magnetic field, which is created by the field circuit here, then a voltage is induced on that wire. And that is this EB voltage. That is the back EMF voltage is induced. So this is the physical mechanism of a DC motor, how it works. We have basically two circuits, and we apply voltages and currents to both of those circuits. And in the end, we get a rotating rotor and some additional voltage created here. Okay? So this is modeling the rotor here, and this is the back EMF voltage which is generated by the rotor. So this is the mathematical model, and now we're going to start writing some equations relating this torque and the velocity to the voltage and current variables. So you have to remember only two things when you are working with DC motor. So this relationship is this. So if you are working with a current current is related to the torque generated by the DC motor. Okay, so there is a relation, going to be a relationship between current and torque, and there is a relationship between voltage and the angular velocity. Okay, so you have to just remember there are such relationships between these variables. There is a relationship between current and torque, and there is a relationship between voltage and angular velocity. So now I'm going to write the terminal equations of a DC motor. So the torque generated by a DC motor is given by the following. I have a constant here that is called K tau, and the torque generated by the DC motor is proportional to the multiplication of the field current times the armature current. Okay? So there is a relationship between current and torque. So I have two currents here. They are multiplied, and the result is multiplied by a constant, and this gives me the torque generated by the DC motor. This torque. Okay? So torque is related to the current, both of the currents here. And these currents are entering into this relationship with a multiplication. So there is a nonlinear relationship in general. If IF and IA are changing at the same time, this relationship is just a nonlinear relationship, which is not good for us. So we're going to see how we avoid this type of multiplicative nonlinearity while working with DC motor. Okay? And the second relationship is going to be a relationship between voltage and angular velocity. And this relationship is given by this. EB, the back EMF voltage induced by the DC motor, is given as KB times the angular velocity of the DC motor. Okay? So these are the only two relationships that you need to remember while working with a DC motor. So current generates a torque, speed generates a voltage. All right? So as I told you, there is a nonlinear relationship in this torque relationship. And we really don't like working with nonlinear systems. As a result, while working with a DC motor, we always keep one of these currents to be a constant. So while working with a DC motor, we always keep one of these currents, either IF or IA, we keep one of them to be a constant. Okay? We never change one of them while working with a DC motor or while controlling a DC motor. So this gives us two ways to actually control a DC motor. Either I can keep IF constant and I change IA to control the torque, or I can keep IA as a constant and I change IF to control the torque. Okay? Remember that we can change both of these currents at the same time, but we never do that. So either I keep the field current to be a constant and I change IA to control the torque generated by the motor, or I do the reverse. I keep the armature current to be a constant and I change IF in order to be able to control the torque of the motor here. Okay? So these two types of control has different names. One is called armature control and the other one is called field control. Two ways to control a DC motor. The first one is the armature control. Second one is the field control. Let us look at the equations of these types of control. So if I have an armature controlled DC motor, then what I do is that I keep the field current constant. So I keep this current constant and I change IA to change the torque of the motor. Okay? So in this case, IF, the field current is kept constant. IA is changed to control the DC motor. Okay? In that case, what would be the equations of the DC motor? So here, when I look at this equation, this is constant. When I apply armature control, IF is a constant. So the multiplication of these two constants will be a single constant. Okay? IA can change, so tau is going to be a constant times the armature current. So in this case, the equation for the DC motor, I will call the multiplication of K tau IF, which is going to be a constant, as K tau A. So this is the constant of the armature controlled DC motor, torque constant of the armature controlled DC motor times IA. Okay? So this equation turns into this linear equation in this case. This nonlinear equation in general turns into a linear equation when we apply armature control, when we keep the field current to be a constant. Okay? And the second equation is the same. There is no change there. EB is equal to KB times omega. Okay? And the second type of control is called field control. Field control DC motor. Okay? And in this case, we do the reverse. I keep the armature current constant in this case. IA is kept constant and IF is changed to control the DC motor. Okay? In this case, I keep this current constant, IA constant, and I change IF in order to be able to control the torque. And now what do we have? In this case, I have again the same nonlinear relationship, but I keep IA as a constant and K tau is a constant. So K tau times IA is a constant, which gives me the following torque relationship. The torque generated by the DC motor is K tau field, torque constant of the DC motor when we use field control is times this IF, the field current, the changing current. Okay? And in this case, the other equation remains the same as well, but usually we don't use it at all. Because this current is kept at a constant, really we don't need to worry about EB anymore. So this is the only equation that is required when you apply field control to a DC motor. Okay? So that is the mathematical model. So you need to remember this. Torque is always related to the current. Voltage is related to the angular velocity. And the first equation, the second equation never changes. But the first equation, depending on whether IF is constant or IA is constant, we define different coefficients here, K tau A or K tau F, and we work with different currents. In armature controlled DC motor, tau becomes proportional to the armature current. In field controlled DC motor, tau, the torque, becomes proportional to the field current. Okay? So that is the mathematical model of a DC motor. So now I will solve an easy example related to the armature control, and then we're going to solve a much more difficult example in armature control. And finally, I'm going to solve a field-controlled DC motor example, which is going to finish the mathematical modeling part of this course. So here, let us look at an example. Armature-controlled DC motor. So here I will be working with this scenario here. This scenario on the left. So in this case, IF is constant, IA is changed. Okay? So really I do not have to worry about the field circuit anymore, because I am assuming that this IF is kept at a constant value, and really I do not have to care about at all about this field circuit. Okay? Now what I'm going to do is obtain differential equation, transfer function, and state space representation for the system on the left. This system. Okay? And what is the input of the system and what is the output of the system? Let us define those. Input, I will assume that is the armature voltage. VA is the input. So we control this voltage in order to be able to change the velocity of the DC motor. So the output is going to be the angular velocity. Okay? It is going to be the omega variable. All right? And we need to obtain differential equation, transfer function, and state space representations here for the same system. So now first I'm going to write the differential equations relating the DC motor, related to the DC motor system, and then we are going to obtain the transfer function, but we will see that really there will be lots of equations here. Too many equations to think about. And then what we are going to do is that we will use these block diagrams that we have learned in the last lecture in order to be able to calculate the transfer function representation. Okay? So I will first write all of the equations describing the system, which is in some way will be the differential equation representation of the system. And then what I'm going to do is that we will see that the equations will really be too many. And in this example, they are not too many, but in the future examples, there will be too many equations, and we are going to handle those equations by using some concepts of block diagrams. Okay? So you will see how these block diagrams will be used in obtaining transfer functions of such systems in an easier way. So now let us start writing the equations. The first thing I will remind you is that what is the terminal equation of an inductor? Remember, inductor terminal equation is L di over dt is equal to V. This is the voltage falling onto the inductor, and this is going to be L times the time derivative of the current. Okay? So now let us try to write the equations of the armature circuit here. Okay? This is going to be the differential equation representation. In the armature circuit, there will be a voltage on the inductor. It is going to be LA dia over dt. This is going to be the voltage on the inductor. And what is the voltage on the resistor? It is going to be the resistance times the current. Okay? So this is the voltage on the inductor, and this is the voltage on the resistor. And if I sum this voltage, and this voltage, EB, I need to get VA. This is a very, very simple serial circuit. If I sum EB voltage with the voltage on the inductor plus the voltage on the resistor, I need to get VA. Okay? But this is nothing but the sum of these two voltages should be VA minus EB. Okay? This is the same equation that I'm talking about. Voltage on the inductor plus voltage on the resistor plus EB is equal to VA. Okay? I generally write this equation in this form, which is going to be easier to interpret. Okay? This is my first equation. And what is next? Let me write the torque relationship, or let me write what EB is. EB is going to be in this equation, EB is going to be KB times the angular velocity of the DC motor. Okay? What is next? I can write what tau is. Tau is going to be, this is an armature controlled DC motor. As a result, the torque generated by the DC motor is going to be armature current times a coefficient. Okay? We call this coefficient as K tau armature control times IA. Okay? This is going to give me the torque. And then let me write the equations related to this mass here, or inertia. In this case, what I'm going to write is I will first write the equations with the theta variables. Then I will try to use omega variables, okay, instead of theta. Because here, the output of the system is omega here. And theta really is not required from us at all in this system. As a result, even if I write an equation with thetas there, I need to somehow convert it into an equation in omega. So J times theta double dot is going to be net force applied onto this inertia. The first net torque applied onto the inertia. The first torque applied from the outside onto this inertia is the tau that is generated by the DC motor. So this is equal to tau. And there is a friction here, which is represented by B, okay? The friction coefficient B, minus B times theta dot, okay? So this is the equation for this inertia here. And you see that omega only appears here. So, but this theta is related to omega as well. And instead of writing this equation in this manner, I will get rid of theta variables here. And instead, I'm going to use omega variables. So, the relationship between omega and theta is this. Omega is equal to theta dot. Omega is the time derivative of theta. So, instead of writing this equation like this, I will write it like this. J times theta double dot in terms of omega is just omega dot. Okay? That is equal to tau minus B theta dot is just omega. Okay? So now I won't use this equation anymore. I really do not need it anymore. I will just use this equation, this one, and this one to obtain the mathematical model. And these are all of the equations that I can write actually for obtaining the mathematical model. And this can count as a differential equation representation here. Of course, we can make some cancellations. We can get rid of some of the variables here, but we will leave it at this point for it to be the differential equation representation. Now let us go into transfer function representation. And of course, for transfer function representation, we need to calculate this G of S, which is the ratio of the Laplace transforms of the output to the input. And in this case, the input is VA of S, and the output is omega of S. This is the capital letter for omega. This is small omega, and this is capital omega. Okay? So what I have to do here, I have to find omega in terms of VA in order to be able to calculate the transfer function. So, of course, you know how to achieve such a task by now, I hope at least. So here, I need to find omega of s. So here what you can do is that try to find omega of s from this equation in terms of tau, and then from tau you go to IA, and from IA you go to VA, and there are some additional variables here, EB, which you need to get rid of. So the algebraic way is usually quite complicated, and you have to work with many substitutions when you try to obtain the transfer function representation for such systems. So here, what I'm going to do is that I'm going to try to form a graphical model, a block diagram for the system, and which is going to give us the transfer function of the overall system in a much easier way than applying algebra and making substitutions in these equations. Okay? But the first thing is going to be to pass all of these equations into Laplace domain. I will do it only for this example, and in the future examples of this lecture, I will ask you to do the same thing in your mind. Okay? It is not going to be something difficult. So here let us pass the first equation into Laplace domain. LA and the derivative is going to be just S plus RA times the current IA of S is equal to Laplace transform of these voltages, VA minus EB. Okay? Here, I won't write parentheses S to each variable. You know that I need to write those, but I will skip them for the sake of brevity. You need to know that there should be S's in each of these variables. So let me pass the second equation. It is very easy to pass the second equation into Laplace domain. EB is equal to KB times omega. Okay? And tau, I don't know what capital tau looks like, so I will write just this strange t here. T is going to be, tau is going to be k tau a times IA. And I finally have this last equation to pass into Laplace domain. And how I am going to pass it into Laplace domain is going to be like this. I will take this b omega to the other side. This is going to give me Js plus b omega of s, Js plus b omega of s is equal to just tau. Okay? Now all of the equations are in the Laplace domain. Now I can continue in order to be able to obtain the transfer function of this system. I will erase these parts so that I have some wide area to write. So here is what we have to do. In order to be able to calculate the overall transfer function of this system, I will here draw a block diagram starting from the input variable. Input variable is VA, okay? The armature voltage. And this block diagram is going to end at the output variable. And this output variable is going to be omega. Okay? And then I will try to fill in this block diagram, starting from the input, ending at the output. Okay, I will draw some blocks, put some blocks here, and then I will try to obtain the overall transfer function of those blocks by simplifying them, using the feedback rule. So here, the first thing that I'm going to do is that from VA, the first thing that I will do is that from VA, I am going to go into the armature current. From VA, I'm going to go into the armature current. But how can I go from VA into the armature current? I need to know also the additional voltage EB, and EB is related to the omega. Okay? So here I have some strange situation. In order to calculate IA from VA, I need to know what EB is. So here is what I'm going to do. I know that in order to calculate IA from VA, I need to subtract EB from VA, and then I need to divide the result with LAS plus RA. Okay? So since I don't know EB here, I will just add here a subtraction operation. So this is going to be a subtraction operation, and I will here write the EB variable. I don't know what this is, but my aim is going to be to complete this EB branch at the end, when I come to the end. Okay? So here, this variable here is VA minus EB. Okay? The variable here is VA minus EB. What is next? I know that when I have VA minus EB, if I divide it with LS plus RA, LAS plus RA, if I take this number here from here to here as a division, that is going to give me IA. Okay? So here I will put a single block, and that single block is going to be 1 over LAS plus RA. Okay? And the output of this block is then going to be the IA variable. Okay? So what did I do? Subtracted EB from VA and then divided by LAS plus RA. That gave me IA. From now I have the variable IA here. From that IA, I know that if I multiply it with a constant, I will go to this torque variable. Okay? So here is my equation. IA times K tau A is going to give me the torque. In Laplace domain, it's similar. So I will put here a constant block, K tau A, and this is going to be the torque variable in this case. And from the torque, now I can go into this output angular velocity. How can I do that? I can do it using this. I need to calculate omega from the torque. But what is that? Omega is equal to torque divided by Js plus B. Okay? Torque divided by Js plus B is omega. Okay? Is this equation at the same time. So I will put here just another block. 1 over Js plus B, and that is going to be my output omega. Okay? Now I have completed most of the block diagram. The only thing missing is what this EB is. I know that EB is related to omega with this equation. Okay? EB is KB times omega, and therefore if I multiply omega with KB, I can find what EB is. So omega is here at the end of the block diagram, and EB is there. So this is going to be a feedback in this case. So I will take a branch here. Into that branch, I will put a multiplier coefficient, which is KB, and I will feed it back into the input side. Okay? So this completes the block diagram that I would have to form here. Okay? Then all I have to do after forming such a block diagram is to calculate the overall transfer function of this system, of this block diagram. So now, how can I calculate the overall transfer function of this block diagram? This is just a simple feedback loop. Okay? And if you remember from the last lecture, we have learned how to reduce such block diagrams to a single transfer function. And that is what we're going to do here. The transfer function of this overall system, G of S, is going to be what was the rule? Forward path transfer function divided by 1 plus everything in the loop. Okay? Forward path transfer function divided by 1 plus everything in the loop. That is the feedback rule. Okay, let us do that. Forward path transfer function is the multiplication of all of these three blocks. okay, K tau A divided by LS plus LAS plus RA times JS plus B divided by everything in the loop, 1 plus, because this is a negative feedback system, 1 plus everything in the loop. I have K tau A, and I will multiply this with KB. KB divided by LAS plus RA, JS plus B here. This is the overall transfer function of this system. And if I equate the denominators in the denominator here, and if I cancel the denominators afterwards, then I will get the following. K tau A divided by LAS plus RA, JS plus B plus K tau A, KB. So this is my transfer function. Okay? So now we have finished the most of the tasks. This is the transfer function representation, and we finally come to the state space representations. Okay? Now in the state space representations, I would need how many state variables? In order to be able to do that, I will look at the order of this system. The order of the system is the order of the denominator polynomial. You see that it is just 2 here. Okay? So my state, there will be 2 state variables, and the state is going to be composed of those 2 state variables. Which variables should I choose here as my state variables? In order to be able to do that, I want you to look at these equations in time domain. Okay? What is a state space representation? In a state space representation, I need to express the time derivatives of the state variables in terms of the state variables themselves plus the input. And here, whatever variables I put here, I need to be able to express those variables in terms of themselves, express the time derivative of those variables in terms of their selves plus the input. Okay? Now here, in these equations, therefore, I need to look for derivatives. I need to be able to express the derivatives from these equations in terms of the other variables. So there is one derivative here, IA dot. Okay? So here, from this equation, you see that I can express the derivative of IA in terms of some other variables. So I will choose my first variable as IA, the armature current. And I also see another derivative here, which is omega dot. And this is expressing omega dot in terms of some other variables. So I will choose omega as my second variable. Okay? And then I will try to write the equations, state equations. So what do I have to do? I am going to use these equations here. So let us try to write the first equation. I need to express IA dot in terms of these state variables plus the input. So LA times IA dot here, this is going to be, it is this term, it is minus RA, this RAIA is going to go to the other side, RAIA, this term is quite fine, it is in terms of the one of the state variables, plus VA, this term is also fine because this was the input, and the third term is minus EB. EB is not one of the state variables, and EB is not the input. So what I need to do here, I need to write EB in terms of the state variables or the input. Okay? But that is quite easy because EB is KB times omega. Okay? So I can just write here minus KB times omega. This is my first state equation. Okay? If I divide this equation with LA, then I will get my first state equation. Let us write the second state equation. So I will, in order to be able to do that, I will use this j omega dot. J omega dot is going to be tau. Tau is not one of the state variables. It's not in terms of IA, omega, or the input. So here is what I'm going to do. I will write tau also in terms of the state variables and the input. And it is given by this equation. Tau is equal to k tau A times IA. K tau A times IA here. And now this tau is related to one of the state variables, minus b times omega is already related to the state variables. So these two are going to form my state equations. Okay? So let me write the state space representation. So I have here x dot is equal to x plus bu and y is equal to cx. Okay? So x dot, the first row is going to be ia dot. Ia dot is this coefficient times ia. The coefficient of ia here is going to be ra over la. And the coefficient of the second state variable will be minus kb over la. And the coefficient of the input will be 1 over la here. And the second rows are going to be formed from the second equation here, and that is going to be v omega dot is going to be ia times k tau a over j, k tau a over j, and minus b over j times omega, and there is no input component. Input is va in this system. Okay? And the output equation, no input in the output. So the output of this system is omega. That means that I will put here just 0, 1. Okay? So that completes my example here. So we have finished our first example. And now we're going to go into a more complicated example. It is again an armature controlled DC motor, but the example will be more complicated. It's going to be looking like this. It is again an armature controlled DC motor. In this case, there are no subscripts in the resistor and the inductor in the armature. So we have the input voltage V here, and I have the armature current IA. And sometimes electrical engineers show that this is an armature controlled DC motor in the following way. And sometimes we write constant here. Okay? This is the field circuit of the DC motor, and we actually connect a constant voltage here. This is the constant voltage sign here in electrical engineering, and this means that IF is a constant here. So that this is an armature controlled DC motor. That is what this is showing. And I have some back EMF voltage here like this. And the rotor is connected first to a mass given like this, that is called Jm, and maybe I need to erase a little bit more here. And this Jm is connected to a gear. Okay? This gear is going to have the ratio 1, and I will have N here, and the gear on this side is going to be connected to a load. This is called JL. And there is going to be a friction between the JL and the ground. So this is the friction BL. All right? So now I can actually define some variables here. So here, these variables here in this direction are going to be theta m, omega m, and tau m. And the variables here are going to be theta g, omega g, and tau g. And the variables here are going to be theta L, tau L, and omega L. Okay? I think these are all of the variables. So I will define the input of this system as the armature voltage V. This is my input, is the voltage, and the output is going to be the theta L. That is the angular displacement of the load here. Okay? So here when you define torques in these systems, or when you talk about some forces or torques in these systems, you need to be really very, very careful about which element is applying that force or torque to which element. And here I want to be very clear about this. So this tau m is going to be the torque applied by motor onto Jm. Okay? And this tau g, what I define there is the torque applied by Jm, by this inertia, onto this gear, onto the gear. Okay? And finally, this tau L is torque applied by the gear onto JL. Okay? So these are the definitions of these torques. So remember here, when I try to write the equation of an inertia, I need to count the torques applied onto this inertia. Applied onto this inertia by some outside forces. So tau m is applied onto this inertia, but tau g here is applied by this Jm onto gear. Okay? When I try to write tau net on this Jm, I need to count the torques applied onto this Jm by the outside elements. Okay? This tau m is applied onto Jm by the motor, but tau g is what this Jm is applying onto the outside world. If I apply a force, if some mass applies a force onto another mass, the opposite of that force is applied onto the original mass by the outside mass here. If I push something like this, some mass, that same mass applies the same force to me. Okay? For every action, there is a reaction. So here, tau m is applied onto this inertia by the motor, but tau g is applied by Jm onto gear. So then what is the torque applied by this gear onto this Jm? If tau g is the torque applied by Jm onto gear, the torque applied by the gear onto Jm is going to be negative tau g. It's going to be minus tau g. Okay? So I have to be very, very careful here because of these definitions of these torques here. Okay, when I try to work on inertias or masses, I should always count the torques or forces applied onto those masses or inertias by the outside world. If mass or the inertia is applying a torque to the outside, then I have to take their negative when I try to write the net force or torque into that equation. So this was something critical that we're going to use. So now let me try to write the equations. The task is the same. Find differential equation, transfer function, and state space representations. All right, for this system. So here is what I'm going to do. I'm going to start from the left, and then we'll go towards the right until the end. So here let me first write the equations related to the armature current. So I will start with the voltage on the inductor, L dIA over dt, plus voltage on the resistor, R times IA. This is going to be, again, V minus EB. Okay? V minus EB. Because the summation of the inductor voltage, resistor voltage, plus EB should be V. Okay? This is my first equation, and it is the same as the earlier example. Actually, earlier example was only this part of the example. And here in this example, what are these things representing? Jm represents the inertia of the rotor of the DC motor. Okay. Sometimes we put also a friction here to represent the friction of the rotor with its surroundings. Okay. Then, in order to connect the motor to some outside loads, we use some gears here with the ratio 1n here, and we connect the other side of the gear to some load here that we would like to turn. So here, this thing, so what is the electric motor here? Electric motor is in this circle here. Okay? So this part is the shaft of the electric motor, and this is representing the inertia of the rotor of the motor. Okay? So now let me write other equations here. So I can actually write what tau m is. Tau m is equal to, this is an armature controlled DC motor, K tau A times, I have the armature current. Okay? And I know what EB is. EB is equal to KB times the speed of the, or angular velocity of the motor, it is omega m. So this is a rigid body, okay? So I have a rigid body here, and this rigid body has some displacement on this side and has some other angular displacement on the other side. These two displacements should be the same because this is not really a spring. So this is not elastic. This is a rigid body. If I turn one side, the other side will turn in the same way. So actually these variables, theta m and omega m, and theta g and omega g, they should be equal to each other. Okay? So I have theta m equals to theta g, and omega m is equal to omega g. Maybe I should write it to the right. Omega m is equal to omega g. Now let me try to write the equations of this Jm. Jm times, so here is what I'm going to do. I'm not going to actually write here theta m double dot. Okay? I will write these equations only in terms of angular velocities, and I will keep the derivative orders in my equations to be at 1. Okay? In order to be able to write the state equations in an easier way, I will keep the derivative orders in my equations to be 1. Okay? So if I use theta m here, I need to put double dots. Okay? That is why I'm not going to use theta m here. Instead, I will write the same equation in terms of omega m. So this is going to be omega m just dot. This is going to be the net torque applied onto this inertia by the outside sources. So I have this torque applied by the motor onto Jm. Okay? So I will write this tau m here. This is a torque applied onto this Jm by an outside source, by the DC motor. And the second torque is going to come from here. And this torque is the torque tau g. But tau g is not the torque applied onto this Jm by the gear. It is the torque applied by Jm onto the gear. So for every action, there is an equivalent reaction. So what is going to happen is that negative of this torque is going to be applied onto Jm by the gear. And here I am counting the torques applied onto this Jm by outside sources. That is why I need to invert this tau g in my counting the torques. Okay? So here this is going to be minus tau g, and there are no other torque sources applied onto Jm by outside sources. If there were friction here, Bm, what would you do? In that case, I would add one more term here, minus Bm times omega m. Okay, that would just give me an additional friction torque. Okay. Now what is next? I know that theta m dot is equal to omega m. This is one of the equations. And what else? Now I can go into these additional variables here. Let us write theta L in terms of theta G, which is the same as theta M. Theta L in terms of theta M, and tau L in terms of, I will write tau G here. What should be the relationships? So this gear is larger, which means that theta L is going to be smaller than theta G or theta M. Okay? So that is why I'm going to put here 1 over n. The radius of this one is 1, and radius of this one is n. That means that in order to get, if n is larger than 1, then I need to get a smaller angular displacement by the larger gear. That means that I need to put here just 1 over n. And finally, I know that the torque relationship is going to be the reverse relationship. So 1 over n is the coefficient here, so the coefficient here should be just n. All right? And what is the relationship between omega L and omega G or omega M? The relationship between those should be the following. Just take the time derivatives of these two variables. 1 over n is constant. So omega L is 1 over n omega M. Okay? And the final equation here is going to be the equation of this JL. So I will do a similar thing there. JL times, instead of writing theta L double dot, I will write, maybe I should write it down here. So JL times omega L dot. This, if I write here theta L double dot, it is going to be equivalent. And if I want to write it in terms of omega L, I would put J omega L dot is equal to torque applied onto this inertia by the outside sources. Tau L is the torque applied by the gear onto JL. So I will add here tau L minus the friction force, BL, and I would have the omega L variable here. Instead of theta L dot here, I will write BL omega L. And finally, I need to calculate what theta L is, and it is going to be calculated by theta L dot is equal to just omega L. Okay? So these are all of the equations that I can write for this system. And now what we are going to do is, so this completes the differential equation representation. Okay? In general, when we have this many equations, I really do not want to find a single differential equation that involves only the input and the output. So I would leave this at this to be the differential equation representation, and then I would start calculating the transfer function. Okay? For that, I will erase these. So now let us start the transfer function representation. So in the transfer function, as I have told you, I will start from the input. The input of this system is the voltage V, and I will end this at the output theta L. Okay? So I will fill in the blocks here to obtain the transfer function. Okay? So now let us start from the first equation. V, in order to go from V into the current here, I need to subtract EB here, but I don't know what EB is. EB is related to some other variables. As a result here, I will define a missing variable here, which is going to be EB later when I find the other parts of this system. And then the variable here is going to be V minus EB. Okay? And then I will put a block here, and this block has to give me the current IA. Okay? Now I want you to pass this equation into Laplace domain in your mind. Okay? I don't want to write the Laplace domain equation here. It's going to be the same as the one that we have found in the previous example. It is going to be Ls plus R times IA is V minus capital EB. Okay? So if I divide V minus EB with Ls plus R, that is going to give me IA. As a result, this block here is going to be Ls plus R. 1 over Ls plus R. And this is going to be the current in the armature. And from this current, I know that I can go to this torque. How I can go there? By multiplying this with the torque constant. If I multiply the current with K tau A, then I would go to the torque. K tau A. So this is going to be my torque, tau M. Okay? From tau M, I want to go to some other variables. You see that from tau M, I can go to omega M. And omega M is quite good actually, because between omega M and omega L, there is such a simple relationship, and omega L is related to the output theta L with this relationship. Okay? So, but in order to go from tau M to omega M, I need to first subtract tau G from tau M, and then I need to go into omega M by dividing the result with JMS. Okay? But first I need to subtract tau G, and I don't know what tau G is here at this time. So here what I do is I put one more subtraction here, and that is going to be my tau G. All right? And the difference here is going to be tau M minus tau G. And how can I obtain omega M from this subtraction? I can actually just divide this by JMS to obtain this result. Okay? So here I put 1 over JMS block, and that is going to give me omega M. Okay? Maybe I need to shift this a little bit to the right. So this is theta L. So now from omega M, I can go to omega L. Omega L is something that I like because I need to end here at theta L. Okay? So I multiply this with 1 over N, and then this becomes omega L. Okay? And from omega L, I need to go to theta L. Look at this equation. Theta L dot is equal to omega L. how can I pass this equation in your mind into Laplace domain? S times theta L is capital omega L. So theta L is 1 over S times omega L. Okay? So I put just 1 over S here. All right? So now we have completed the forward path of this block diagram. So we started from the input and we ended at the output. Now what I have to do is I need to complete all of these other missing variables. All right? EB and tau G. So the first thing that I'm going to do is to complete this EB. EB is KB times omega m. So I take omega m here, and then I multiply it with KB, and I supply it back. So this completes one of the missing variables. And the second variable is going to be related to this tau G. Okay? So I have this tau G here. And I have some variables here, omega L and theta L here. So this equation still I haven't used, so I can look at this equation. If I pass this equation into Laplace domain, JLS plus BL times omega L is equal to tau L. Okay? And tau L is equal to n times tau G. Okay? From this equation, I can write tau G is equal to 1 over n tau L. So here, what I can do is that I can start with omega L here. Maybe I should draw it a little bit below. So I will take this to the bottom. So this is KB. And finally, I take omega L here, and if I multiply omega L with JLSBL, then I get tau L, JLSBL, and this gives me tau L. And finally, if I multiply tau L with 1 over n, that gives us tau G. Okay? 1 over n here, and that gives us tau G. Okay? So we have completed the system here, and all I have to do in order to be able to find the overall transfer function is to find the overall transfer function of this system. Okay? So you see that unfortunately the block diagram that we have found here is not really that simple as the earlier example. So it is not as simple in this case. So I have to make some modifications here before I can calculate what the overall transfer function is. But all of those modifications would become straightforward manipulations, and then the probability of making an error is actually lower in this case than dealing with all of these equations at the same time. Okay? So now, how can I calculate the overall transfer function of this system? It is not really easy, because here I really do not see a feedback loop in its simple form. So we see that in this larger feedback loop, I have a summation in the middle, and in this smaller feedback loop, there is a branch going out in the middle here, and that is why I cannot apply the feedback rule immediately here. Okay? That is why finding the transfer function of this block diagram is not really that easy. But we know actually how to make manipulations in this case over this block diagram. Okay? So here is what I'm going to do. In order to be able to calculate this the overall transfer function, I want to use the feedback rule. In order to be able to use the feedback rule, I have to apply modifications onto this block diagram. And the modifications that I choose here is going to be the following. I don't really want to draw this block diagram once again, but I'm going to do the modification on this one by changing some parts. So I want to take this branching out here from here to here. Okay? So I want to take this from here. I want to erase this branching out from here, and then I want to add it here. Okay? So instead of branching out from here, I'm branching out from here. But what is the change that I did while I tried to do that? So instead of branching out from here, I'm now branching out from here, and that changed this system. How did it change? How can I compensate it? So I can compensate the modification here by adding an additional block here, 1 over n. Okay? In the earlier original block diagram, this signal was passing from 1 over n and it was going towards here. Now it is going directly to here. Okay? Therefore, in order to be able to compensate this change from here to here, I need to add here a 1 over n. Okay? This signal should still pass through 1 over n while going to this block here. But putting here a 1 over n is nothing but adding an extra 1 over n here on this line. Okay? That is why what I'm going to do is I will just put a square here. Okay? So this is going to be 1 over n squared. If I put here 1 over n, it is the same as putting a 1 over n here, anywhere on this line here. That is why I will change this 1 over n into 1 over n squared. This is still going to give the same overall transfer function. Okay? Now I need to erase this, unfortunately. So now I can calculate the overall transfer function of this system. I have a smaller feedback loop here inside, and I have a larger feedback loop. So I have to apply feedback rule twice in order to be able to calculate the overall transfer function here. Now the first thing is this smaller feedback loop. It looks like this, 1 over JMS, and I have here JLSBL divided by n squared. Okay? This is the smaller feedback loop here. Let us first calculate what this is equivalent to. This is equivalent to forward path transfer function 1 over JMS divided by 1 plus, this is a negative feedback loop, everything in the loop. Okay? 1 over JMS and JLS plus BL divided by n squared. Now I'm going to equate the denominators here. So I will just take this term to here and then cancel JMS's. This is going to give me the following. 1 over JMS plus JL over n squared S plus BL over n squared. Now I will collect the S terms and the constant terms. 1 over Jm plus JL over n squared S plus BL over n squared. Now in order to make some simplifications, I will call this as J equivalent and I will call this as B equivalent. Okay? So Jm plus JL over n squared is called J equivalent, and BL over n squared is called B equivalent. Then this is going to be equivalent to 1 over J equivalent S plus B equivalent. Okay? So it is what this block is. Okay? So I can replace this complicated block with this transfer function, 1 over J equivalent S plus B equivalent. Okay? And then I can continue calculating the overall transfer function. I'm not really using the board in a fine way here, so unfortunately I ran out of place there, so I will have to write to this corner. I know that, sorry, it is not really a good use of the board, but I would have to do it like this. So now let us calculate the overall transfer function of this larger feedback loop. The forward path transfer function is going to be this. G of S. The forward path transfer function is going to be everything in this forward path. Okay? So it is going to be K tau A divided by, I would have here Ls plus R, and finally here I have J equivalent S plus B equivalent. Plus B equivalent divided by 1 plus, I have everything in the loop. Okay, so KB times what I have written there. So K tau A KB divided by Ls plus R, J equivalent S plus B equivalent, and that is all here. Okay, so this is what this larger feedback loop is. If I want to complete this larger feedback loop to the transfer function of the overall system, then I need to multiply with these two as well. So these are going to give me the multiplications 1 over n times 1 over s. Okay? So this is the transfer function of the overall system. Now let me make some cancellations. That is going to be K tau A divided by, I will make some cancellations here after equating the denominators, S plus B equivalent, and plus K tau A KB times 1 over n, 1 over s. I hope you can see this. So this is the overall transfer function of this system. Okay. Now this completes the transfer function finding part. The next part is going to be finding the state space representation. For that, I need to know what the order of this transfer function is, or what is the order of this system. And in order to be able to do that, I need to know what's the order of the polynomial in the denominator. And you see that there is this multiplication Ls plus R, J equivalent S plus B equivalent here. And it is further multiplied with S in the denominator. Okay? That means that here, the order of this system is just equal to 3. Okay? Because there is a third order polynomial in the denominator. So I would need 3 state variables to represent this system. So here is what I'm going to do. I'm going to define my state variables. X is equal to, which state variables should I use here? Okay? So I'm going to write the derivatives of the state variables in terms of state variables and the input. Okay? I need to write the derivatives of the state variables in terms of the state variables themselves and the input. So I'm going to use these equations in order to be able to do that. So I'm going to look for derivatives here in these equations, and those derivatives will help us in writing the state equations. The first derivative that I see here is IA. I'm going to add IA as one of my state variables, and the second derivative that I see is omega m, but also there is an omega L here. So which one should I take? It really doesn't matter here. So because omega L and omega m, they are just related with some proportionality constant here. It really doesn't matter which one you take. You can take any of them, but you have to use only one of them. You cannot take both of them because they are related to each other with a linear relationship, with a proportionality constant here. So you can take only one of omega L or omega M. Here I will choose omega M. Okay? And finally, I have the last derivative appears here at theta L. And I will put theta L as my last state variable. So as you see, when you write your equations by keeping the derivative order at most at 1, then you can find these variables quite easily by looking for the first order derivatives in your equations. And here I have theta L dot and theta M dot. Which one I'm going to take, it really doesn't matter. As long as you take one of them, you are really fine, but you have to take at most one of them. You cannot use both of them because they are related to each other with a proportionality constant like this. So I have my x like this. So now let us write our state equations. The first state equation is going to be related to this IA. So L times IA dot is equal to, I will take this RIA to the right hand side, RIA. This is still related to the state variables. And I have plus V minus, instead of EB here, I need to write something related to the state variables or the input. This is my input. And instead of EB, I will write just this one. And this is already related to omega M, as you see. So as you see, I have here KB omega M. Okay? This is going to give me my first state equation. Let us look at the second state equation. It is going to be related to omega M, and this is going to be actually more difficult. So Jm omega M dot is equal to tau M. Tau M is neither an input nor a state variable. Therefore, I need to write it in terms of state variables and the input. And I see that tau M is written as k tau A IA here. So I have k tau A IA minus tau G is not a state variable, nor it is an input. So I have to write it again in terms of the state variables or input here. Here is what I'm going to do here. Instead of tau G, I will write 1 over n tau L. And I will extract tau L from this last equation. And I have omega L here. So this is going to be k tau A IA minus 1 over n. Instead of tau L, I am writing JL omega L dot minus or plus BL, I would have omega L. Okay? Now I can write what omega L is in terms of one of the state variables. My state variable is omega M, and I know that omega L is 1 over n omega M. Okay? So instead of this omega L dot, I am going to write 1 over n omega M dot, and instead of this omega L, I will write 1 over n omega M. Okay? So this is going to be k tau A IA minus, here in front of both of these terms there will be a 1 over n, so there will be a 1 over n square here. It is going to be JL omega M dot plus BL omega M. Okay? So now let us look at this equation. Jm omega M dot is equal to this thing. Okay? And here what do I have to do? I need to express omega M dot in terms of the state variables or the input. And here I have one more omega M dot, and I will take it to the left hand side. So here Jm plus 1 over n squared JL omega M dot is equal to, I would have k tau A IA minus BL over n square omega M. Okay? And I know that I have already defined this coefficient as J equivalent, and this is B equivalent. Okay? So I will write the equivalent equation for this one like this. J equivalent times omega m dot is equal to K tau A IA minus B equivalent times omega m. Okay? So this is, as you see, this is like a second state equation. Omega m dot is expressed in terms of two of the state variables, IA and omega m. Okay? And the third state equation is going to be related to, sorry, this is going to be not omega L, omega m. Let us say that this is omega m, because it's going to be easier that way. Okay? Because omega m dot is so this is theta m dot is equal to omega m. Okay? So instead of taking theta L, this one, I will just write theta m, and then theta m dot is going to be omega m. So I would have theta m dot. This is going to be related to my third state equation, and it's just going to be this simple relationship. All right? So I would have which equations here? So this equation will be useful, and this equation would be useful, and finally this equation would be useful. So as an exercise, I can give you the following. So instead of omega m and theta m, take these as omega L and theta L, and try to write the state equations with those variables. What is going to change in that case? So maybe I can erase this part and try to write my state equations. Let us write the state equation. X dot is equal to AX plus BU, and Y is equal to CX. And D is going to be 0 in this case as well. Okay? So the derivative of my first variable is IA dot. And IA dot can be written as minus R over L times IA and minus KB over L times omega m. And there is an input. Input is V here. And I put 1 over L here and 0 here. And omega m dot is given by this. It is K tau A over J equivalent. And omega m coefficient is minus B equivalent over J equivalent. And this is 0, 0. And finally, theta m dot is omega m. So this is 0, 1, 0 here. And I would have 0 here. And what about the output? I have times U here, and the input coefficient is going to be 0. What was the output of this system? The output of this system was theta L. So theta L was the output, but you see, theta L is not one of my state variables. But can I find theta L as a linear combination of these state variables? And the answer is going to be yes here. Okay? And we know that theta L and theta M are related to each other like this. So it is theta L, the output is 1 over n times the third state variable. Okay? So I will put 0, 0, 1 over n here, which would complete my state space representation. So you see here, if you change omega m and theta m, you can also make combinations here. Instead of omega m theta m, you can take omega m theta l, or omega l theta m, etc. And as I told you, as an exercise, try omega L and theta L and try to extract these equations. And here, in that case, you would obtain 0, 0, 1 here, because theta L would be, in that case, the third state variable. So this completes my second example. And unfortunately, I have spent too much time in both of these examples. And As a result, I want to leave the third example, which is the field-controlled DC motor example, to next week. So I'm going to stop here, and you can look forward to the third example, which is the field-controlled DC motor example, which we are going to handle next week. Thank you for watching. Bye-bye.